The configuration of the B-21 Raider for a single pilot with a weapons systems officer reflects a transformative approach to how modern long-range strike aircraft are designed, integrating multiple layers of automation, artificial intelligence, and adaptive digital systems that collectively reduce the human workload while increasing operational flexibility and survivability. Unlike older bomber designs that relied on multiple crew members to manage navigation, sensor operations, communications, and defensive countermeasures, the B-21 shifts much of this responsibility onto highly advanced software and networked computing systems. This means that the pilot and weapons systems officer are freed from routine operational tasks and can focus on high-level decision-making, threat assessment, and mission execution. The aircraft itself acts almost as an intelligent partner rather than just a vehicle. Central to this design is a robust flight management and automation system. The aircraft likely uses multiple redundant autopilot channels capable of managing all phases of flight, including takeoff, long-distance navigation, in-flight course corrections, and landing procedures. These systems are designed to react faster than a human could to changing flight conditions, engine performance fluctuations, or system anomalies. Sensors continuously feed data about airspeed, altitude, environmental conditions, engine health, and system integrity into a networked processing hub. The system prioritizes critical information, filters out redundant or non-essential alerts, and presents the pilot with a simplified, actionable overview. This prevents cognitive overload, which is crucial on long-range missions where situational awareness must be maintained over extended periods. In addition to flight automation, sensor fusion plays a key role. The aircraft's onboard computers integrate multiple types of sensor data, such as radar, infrared detection, electronic signal detection, and environmental readings, to produce a coherent operational picture. Rather than requiring the crew to interpret raw sensor outputs individually, advanced algorithms consolidate the data into intuitive displays highlighting potential threats, safe navigation corridors, and environmental hazards. The system can also predict potential engagements by analyzing trends in electronic emissions or other signals, giving the crew advanced notice and allowing them to make decisions proactively rather than reactively. The automation extends to mission planning and in-flight adaptation. The B-21 is designed to operate in dynamic environments where threat landscapes can change rapidly. Its onboard systems can autonomously adjust routes to avoid detection zones, minimize exposure to countermeasures, and maintain mission objectives. These changes are proposed to the crew, who can approve, modify, or override recommendations. This division of labor allows the aircraft to make rapid tactical adjustments while keeping human judgment at the center of strategic decision-making. Long-duration missions over contested environments particularly benefit from this capability because the aircraft can optimize fuel consumption, evade detection, and maintain optimal operational readiness without constant direct input from the crew. Network integration further expands the aircraft's capabilities. The B-21 is envisioned as part of a broader operational ecosystem where it can communicate with other aircraft and support systems in real time. It can exchange situational awareness data, coordinate surveillance or reconnaissance assets, and act as a control node for other platforms, such as uncrewed vehicles. Automation in this networked environment reduces the need for continuous human intervention, allowing the crew to focus on mission-critical decisions rather than micromanaging subordinate platforms. The onboard systems handle bandwidth management, encryption, and secure data routing autonomously, ensuring that information flow remains reliable and timely even in contested electronic environments. Safety, redundancy, and fault tolerance are also critical in a single-pilot aircraft. Redundant flight control systems, backup computing nodes, and automated recovery protocols allow the aircraft to continue operating safely even in the event of system failures or pilot incapacitation. These redundancies are essential because reducing the number of human crew members inherently reduces the natural redundancy present in multi-crew aircraft. The systems are likely capable of stabilizing the aircraft, maintaining course, or returning it to base autonomously if necessary, while alerting the crew to any problems in a clear, prioritized manner. The software architecture itself is modular and designed for adaptability. This means the B-21 can integrate future upgrades in automation, mission planning, sensor processing, or electronic protection without requiring a complete redesign of the aircraft. Modularity also aids in maintaining cybersecurity, as individual subsystems can be isolated, updated, and secured independently. Because the aircraft relies heavily on complex algorithms to manage critical functions, rigorous verification and validation processes ensure that automation behaves predictably and safely across all scenarios. This reduces the risk of unintended actions in complex operational contexts. Automation also affects how the aircraft manages weapons systems. While the crew retains ultimate authority over deployment decisions, the onboard systems can manage targeting inputs, optimize release parameters, and ensure adherence to mission objectives. By automating routine calculations and threat evaluations, the B-21 allows the crew to focus on strategic choices rather than mechanical execution. This reduces human error and enables faster response times in rapidly evolving operational environments. Ultimately, the shift to a single pilot configuration with a weapons systems officer reflects a broader philosophy. Aircraft of this generation are designed as integrated, intelligent systems rather than simply human-operated vehicles. The crew acts as commanders and overseers, relying on the aircraft's autonomous systems for operational, tactical, and logistical support. The B-21's design anticipates that future operational contexts will demand longer-range missions, higher survivability in contested environments, and the ability to process and act on massive streams of data, all while keeping the crew load manageable. The combination of intelligent automation, adaptive mission management, networked coordination, and fault-tolerant design allows the aircraft to operate effectively with a reduced crew without sacrificing safety, situational awareness, or operational flexibility. This approach also opens the door to future developments where the aircraft could potentially operate without a human crew under certain circumstances. While current doctrine emphasizes human oversight for strategic and ethical decisions, the underlying systems are structured to handle autonomous operations in flight management, navigation, sensor integration, and threat response. By designing the B-21 as an inherently modular, adaptable, and intelligent system, the aircraft not only meets current mission needs but also prepares for future operational concepts where human involvement might be reduced further. The B-21 represents a shift in which the pilot and weapons systems officer are less operators of mechanical systems and more commanders of a highly capable, intelligent, and semi-autonomous machine. The aircraft's digital infrastructure, sensor integration, automation of routine and complex tasks, and networked capabilities create a platform where human decision-making is amplified, supported, and protected by technology, allowing the B-21 to execute long-range, high-risk missions with fewer crew members while maintaining operational effectiveness and safety.